Okay, let's dive into one of the greatest scientific detective stories of all time. Seriously. It's a story that starts with something super simple, an apple falling from a tree, and ends with, well, with the most powerful and mysterious things in the entire cosmos, black holes. This is the story of gravity, the invisible rulebook for our universe. But let's start with the big question. What is gravity really? I mean, we feel it every second of every day, right? It keeps us glued to the planet. But for centuries, figuring out what it actually is was one of the biggest unsolved mysteries in all of science.
So, our story kicks off way back in the 17th century. And our first great detective is, of course, Isaac Newton. This guy was an absolute genius. He figured out what gravity does, but he left behind a huge puzzle about how it does it. And that puzzle, it would take almost 300 years for someone to solve.
And just look at that gap. For nearly 300 years, Newton's idea was the law of the land, no questions asked. It took another brilliant mind, Albert Einstein, a solid decade of intense, head-scratching work to come up with an idea that would completely flip our understanding of the universe on its head.
You know, what Newton figured out was, honestly, mind-blowing. He realized the exact same force that makes an apple fall to the ground is what keeps the moon circling the Earth. He even came up with a formula that could predict it with insane accuracy. But there was one thing that just bugged him. How did it work? How could the sun reach out and pull the Earth across millions of miles of totally empty space? It was like some kind of spooky, invisible action. A total mystery.
And this is where our second detective, Albert Einstein, walks onto the scene. And get this, he wasn't some famous professor at the time. He was a clerk working in a patent office in Switzerland. And his big breakthrough didn't even start with gravity. It started with something totally different, light. Through his work, Einstein discovered a fundamental, unbreakable rule of the universe, a cosmic speed limit. He proved that nothing, and I mean nothing, no object, no message, no anything, can travel faster than the speed of light. And this one simple fact was about to cause a huge problem for Newton's theory of gravity.
So, to see why, let's just do a little thought experiment together. Imagine, right now, the sun just, poof, vanished, gone. What happens to us here on Earth? And more importantly, when would we feel it?
This is where it all goes sideways for the old theory. See, according to Newton, gravity's pull is instantaneous. The second the sun disappears, we'd feel it and our planet would fly off into deep space. But Einstein knew that was impossible. The information that the sun is gone can't travel faster than light. And since it takes light about 8 minutes to get from the sun to us, we wouldn't know anything was wrong for a full 8 minutes. Both of these ideas couldn't be right. Something had to give.
So this paradox just obsessed Einstein. He quit his job, and for 10 years, he did nothing but wrestle with this problem. And then he came back with an answer so revolutionary, it changed everything. It was his theory of general relativity, and it was a solution that nobody saw coming. Okay, so first, Einstein told us to stop thinking about space and time as two different things. He said they're woven together into one single, four-dimensional fabric that he called spacetime. You can kind of think of it as the stage where the entire universe performs. And here it is, the big aha moment. Einstein's big idea was this. Gravity isn't a mysterious, invisible force pulling on things at all. He said gravity is simply the shape, the curvature, of space-time itself. It's not a force in the universe. It's the actual geometry of the universe.
The best way to picture this is to imagine space-time as a giant, stretchy rubber sheet. Now, if you take a heavy bowling ball, that's our sun, and put it in the middle, what happens? The sheet bends, it warps, it creates a big curve. Okay, now roll a little marble, that's the Earth, nearby. It's not being pulled by the bowling ball, it's just following the curve in the sheet. And that path it takes, that is what we feel as gravity. So this new way of thinking didn't just solve that whole vanishing sun problem. Oh no, it gave us a whole new toolkit for understanding the cosmos. From why planets move the way they do to how the most extreme things in the universe even exist. This model perfectly explains why planets orbit the sun. They're not being held on some invisible leash. They're just rolling along the curved path that the sun's massive weight creates in space-time. And here's the kicker. Every single experiment we've ever done to test this theory has proven it right. It lets us explain things that Newton's theory just couldn't touch.
So the logic from here is actually pretty simple. The more mass you have, the deeper the curve you make in spacetime. A planet like Earth makes a little dimple. A star like our sun makes a much bigger one. Easy enough, right?
But what happens if you take an unbelievable amount of mass, like from a giant star that's dying, and you crush it and crush it and crush it all down into a single tiny point? Well, the curve it makes in space-time becomes so deep, so steep, that it basically punches a hole right through the fabric of the universe. And that is a black hole. It's a place where space-time is curved so extremely that all paths lead in. The slope is so steep that once you cross a certain point, there is no way out. Not even for light, the fastest thing in the universe. It can't escape the curve.
So there you have it. We went all the way from a falling apple to understanding that gravity is the literal shape of reality. We now know that matter and energy can actually bend and warp the fabric of the universe, which leaves us with one final kind of amazing question to chew on. If mass can do that, what else is out there that can?